Hello, and welcome to this lecture about support vector machines, or SVM, for classification. Let's start by giving some intuition about how the SVM classifier works. Suppose that we have a training dataset with two classes, the positive class, this one, and the negative class, this one. And suppose that these two classes are linearly separable, so they can be perfectly separated with a linear model, or a line in this example, or more generally a hyperplane if we have more than two features. So the equation of our hyperplane, or our linear classifier, is theta transpose x equals 0. And our hypothesis function, h of x, equals to the sine of theta transpose x. So for given x, if theta transpose x is positive, then we predict the class +1. And if theta transpose x is negative, then we predict the class -1. Now suppose that we want to find the parameters vector theta, or the parameters vector that defines this hyperplane, this linear classifier, so that all the training examples are correctly classified by this linear classifier. An example of such classifier is this one, because this one correctly classifies all the training examples in our training dataset. For example, if we take this data point x, theta transpose x is negative, so the predicted class is -1, and the true class is also -1. If we take this data point x, theta transpose x is positive, so the predicted class is +1. And the true class is also +1. And this is the case for all the training examples. So this classifier basically has 0 error on our training dataset. It correctly classifies all the training examples. Our classifier can also be this line, because this one also classifies correctly all the training examples in our training dataset. Or it can also be this classifier, because it also correctly classifies all our training examples. It can also be any of these classifiers, because all of them also achieve 0 error on our training dataset. But which one of them is the best classifier? To answer this question, let's consider a new data point, indicated with a blue cross here. And this new data point is similar to the data points in the negative class, so it most likely belongs to the negative class. Now let's take this linear classifier, which correctly classifies all our training examples, so it achieves 0 error on our training dataset. But this classifier incorrectly classifies our new test data point into the +1 class. Right? The true label should be -1, but it is the predicted label is +1 because our new data point lies in this half space. It is in this side of the decision boundary. But if we take this green classifier, which also correctly classifies all the training examples, so it also achieves 0 error on the training dataset, then this green classifier correctly classifies this new test data point into the -1 class, because the data point lies in this half space. So what's the difference between these two classifiers, since both of them achieve 0 error on the training dataset? One difference between these two linear classifiers is the so-called margin. So if we take this classifier, or this decision boundary, then the margin is defined as the width that the boundary could be increased by before hitting a data point, or before hitting a training data point. And these training data points that we are talking about, these data points, they are called support vectors. Okay, so for this classifier, this is the margin. And you can see that in this yellow region, there are no training data points. And you can also see that the margin for this classifier is smaller than the margin for this classifier. So this classifier is able to better generalize than this classifier because it has a larger margin. And that's why it correctly classified this new test data point. And in this case, there is a unique linear classifier which achieves zero error on the training dataset and has the maximum possible margin. So there is only one solution or one classifier with the maximum possible margin. If theta transpose x equals 0 is the equation of our decision boundary, and if we are trying to find the parameters vector theta that gives us the maximum possible margin and also correctly classifies our training examples, then there is only one unique solution, one parameters vector that gives us this maximum margin. And as we said previously, these data points here, they are called support vectors. These are data points that the margin pushes up against. And in the simplest version of SVM, we want to find the hyperplane or the linear classifier which has the maximum possible margin. And this classifier should correctly classify all the training examples. So when training, we have two objectives, maximizing the margin and correctly classifying our training examples. Now let's see how to define the optimization problem for this simple linear SVM. We basically have two objectives. First, we want to find the hyperplane with the maximum margin. And second, we want this hyperplane to correctly classify all of our training examples. So we basically want it to have zero training error. We will see later how to relax this second objective in order to allow some misclassification of some training examples. But for now, let's assume that we want this hyperplane to correctly classify all the training examples. Now let's take the first objective. We want to maximize the margin. So let's see how to define this margin. So the equation of our hyperplane is theta transpose x equals 0. And this is our margin. So we have no training examples in this yellow region. And let's say that the first extremity of the margin has the equation theta transpose x equals +1. And the second extremity of the margin has the equation theta transpose x equals -1. And let's take one support vector from one extremity of the margin. It's denoted by x plus, because from this side we predict the class +1. So this is our first support vector, x plus. And another support vector denoted by x minus from the other extremity of the margin. So we know that theta transpose x plus is equal to +1 because this data point x plus lies on this extremity, this line. And theta transpose x minus is equal to -1, right? Because x minus lies on this extremity. Now, based on these two equations, you can multiply the second one by -1 and add them side by side, and you will find that theta transpose x plus minus x minus, so this is a vector difference. So theta transpose this vector difference is equal to 2. The parameters vector theta defines the hyperplane. So it is used in this equation, theta transpose x equals to 0. And this parameters vector theta is a vector which is orthogonal to the hyperplane. And here theta is divided by the norm of theta, just to have a vector of a unit length. And this vector difference, x plus minus x minus, is here. And based on that, the margin M, which is here, is defined as theta transpose x plus minus x minus, this vector difference, divided by the norm of theta. So it's basically a projection of this vector on this one. And since this is equal to 2, so our margin is just defined as 2 over the norm of theta. So as a first objective, we want to maximize the margin. So we want just to maximize 2 over the norm of theta. In other words, we want to minimize the norm of theta so that the margin is maximized. But only maximizing the margin is not sufficient, because you can always choose your parameters vector so that its norm is close to 0. For example, you choose all your parameters to be 0 or close to 0. And in this case, this margin would be very large. But such parameters vector wouldn't be useful, right? So we need some constraints, and this is given by our second objective. So we not only want to find the hyperplane that maximizes the margin, but we also want this hyperplane to correctly classify all our training examples. So we formalized the first objective. We want a large margin, right? But how can we formalize the second objective? We want the hyperplane that correctly classifies all our training examples. We can express this objective as a set of constraints. So for each data point xi in our training dataset, if this data point belongs to the positive class, then we want theta transpose xi to be larger than or equal to +1. So we want it to be correctly classified, right? And if the label of this training data point is -1, it belongs to the negative class, then we want theta transpose xi to be less than or equal to -1. So we want it to be correctly classified. And these two expressions can be simplified in one expression, saying that for each data point I, yi times theta transpose xi should be larger than or equal to +1. So if the label is +1, then we get theta transpose xi larger than +1. And if the label is -1, then we get theta transpose xi less than or equal to -1. So we have n such constraints, one for each training data point. So our optimization problem based on these two objectives is expressed here. We want to find the hyperplane or the parameters vector theta that defines this hyperplane such that the margin is maximized, right? But subject to some constraints. For each training data point I in our training dataset, we want it to be correctly classified. So this is a constrained optimization problem. Now let's see how to solve this constrained optimization problem for this simple version of SVM. So we want to maximize the margin. So we want to maximize 2 over the norm of theta. But maximizing this is actually the same as minimizing the norm of theta. So we can instead minimize the norm of theta. And since the norm of theta is positive, we can actually minimize the norm of theta squared. It's usually easier. And we can also multiply by 1 over 2 because minimizing a function is the same as minimizing some constant times this function. So this is just for mathematical convenience later on when we compute the derivative of the function. So maximizing 2 over the norm of theta, instead of doing this, we can actually minimize 1 over 2 times the norm of theta squared, subject to our previous constraints. We have n constraints. So this is our constrained optimization problem. And we can convert it to a non-constrained optimization problem by using the so-called Lagrange multipliers. So our constrained optimization problem becomes this. We want to minimize our previous function that we want to minimize, this one, right? Minus the sum over all our constraints. We have n of them. So the sum from I equals 1 to n, because we have n data points in our training data set, of alpha I, this is called the Lagrange multipliers. So alpha I times this part here. So this is a non-constrained optimization problem. We just want to minimize all this. And this is our cost function or loss function. And this loss function is a convex function. So there is a unique optimal vector of parameters theta that gives you the minimum possible value for this cost. And we know that the derivative of the cost at the minimum is equal to 0. So to find this optimal parameters vector theta, we can just compute the derivative of the cost function with respect to each parameter, theta j, and put this equal to 0, and then solve for theta. So this is the cost function that we want to minimize. And we have seen in some previous lecture something that looks like this part. In a lecture where we talked about regularization. The norm of theta squared is defined in this way. And by minimizing this, we actually want our parameter values to be small, preferably, in order to avoid overfitting. We have talked about this in a previous lecture. So we are just regularizing our parameters. And to be consistent with the previous lectures, we regularized only all the parameters except theta 0, right? So we do the same thing here. So j starts from 1. So theta hat is the vector of all parameters except theta 0. So we use that here. So we get this cost function. And to minimize this cost function, we need to compute the derivative with respect to each parameter, theta j, and then put this derivative equal to 0 and solve for theta j, right? So the derivative of this function with respect to theta j is given here, and the derivative with respect to theta 0 is given here. So please stop the video if you want to check this for yourself. And putting this equal to 0 means that theta j is equal to this part, right? So we get this. And from this part, we get this. And without going into too much details, by replacing the first equation that we got into our cost function, and by considering the second equation that we got as a constraint, then we will get a new optimization problem which looks like this one. But this time it's with respect to those Lagrange multipliers, the alphas. Okay, so by solving this optimization problem, this constrained optimization problem again, we will find the values of those multipliers, those alphas. And what we will find is that most of them will be equal to 0, and just few multipliers will be non-zero. And each non-zero multiplier indicates that the corresponding xi is a support vector. So we will just get few support vectors. Okay, and what I want you to notice also is that solving this optimization problem involves a dot product between all pairs of training examples. So we have here sum over I and j, and we have here dot product between xi and xj, right? So xi transpose xj. So this is the dot product between two training examples. Okay, so again, by solving this optimization problem, we will find the values of those alphas, and most of them will be 0, and those which are not 0 indicates that the corresponding xi is a support vector. And then if we replace back those alphas into our equations 1 and 2, we will find the values of our parameters. And at the end, our parameters vector will look like this. So this is the vector of parameters theta 1, theta 2 until theta d, if we have d features, and this is theta 0. Now, if we get a new data point x, a new test point, and we want to make a prediction to predict its class, then this is the hypothesis function that we use. So h of x is equal to theta transpose x. And if we replace theta by what we got here in this expression, then we get this expression. And as we said previously, most of those multipliers, those alphas, will be equal to 0. And only few of them will be non-zero, and their corresponding xi's will be called support vectors, right? So this sum actually involves only the support vectors, because most of those terms will be 0. So in order to predict the class of a new test data point x, the prediction involves computing the dot product between this test point x and all the support vectors. Until now, we discussed both simple version of SVM with a hard margin, and we wanted to take into account two objectives. In the first objective, we wanted to maximize the margin. And in the second objective, we wanted to classify correctly all our training examples. So we had a set of constraints. So we wanted basically to get a training error, which is equal to 0. So we classify correctly all the training examples. And so that's a hard margin. So for example, if we get a data set like this one, and some data points are actually outliers, like for example, this one, then if we want to still satisfy these constraints, then we will get a hypothesis which looks like this. So next time if you get a new data point which belongs to the blue class, for example here, then it will be misclassified as belonging to the red class. So maybe instead of getting this hypothesis, what we want is actually a hypothesis which looks like this. Because it achieves a better generalization. And this is what we will see now, how to define a soft margin which allows some misclassification of some training examples. Again, what we saw previously was a simplified support vector machine where we wanted all the training examples to be correctly classified. But this is not always possible because the dataset can be noisy, it can contain some outliers, and sometimes it's not always possible to correctly classify all the training examples with a linear classifier. For example, suppose that you have a data point here which belongs to the blue class, right? So it's not possible to draw a line or to have a linear classifier that correctly classify all those training examples. So instead of considering a hard margin, we can consider a soft margin where we allow some examples, some training examples, to be misclassified. And to do this, we define a new cost function, which looks like this. And this cost function contains two parts. The first part is actually what we had previously. This part expresses the fact that we want to maximize the margin. So as we saw previously, by minimizing the norm of the parameters vector, we are actually maximizing the margin, right? So by minimizing this part, we want to achieve more generalization. And the second part here is the cost for misclassifying the training examples. This part here is the cost or loss for misclassifying one training example. It is called the hinge loss. We will see this shortly after. So by minimizing this, we want to fit our training data in a good way. So we want to minimize the cost for misclassifying the training examples. And by minimizing this part, we want to achieve more generalization because we want a large margin. So this is a trade-off between these two objectives. And this trade-off is controlled by this hyperparameter, C, that we will discuss shortly after. Now let's take this part here. It is called the hinge loss. This is the cost or loss for one training example, xi, with its corresponding label yi. And this part here, theta transpose xi, is the prediction. If our training example belongs to the positive class, it has this label, +1, then this is how the hinge loss looks like. In this case, if our prediction is larger than or equal to 1, then the loss is 0, right? Because we correctly predicted the output, since this data point belongs to the positive class. For example, you get this data point which belongs to the positive class, and our predicted output was something like this. So there is no problem, we correctly predicted the output, so the loss is 0. But if you get a positive example like this one here, and it is misclassified, so the predicted output is something like this value here, then the loss will be very high, right? So in this case, the loss increases linearly. Now the other case, if our training data point belongs to the negative class, class -1, then this is how the hinge loss looks like. For example, if we have this data point which belongs to the negative class, this one, and our prediction is smaller than or equal to -1, for example here, then the loss will be 0, right? Because there is no problem, we correctly predicted the output, right? This data point belongs to the negative class and we predicted something smaller than or equal to -1, so the loss is 0. But if we get a negative example, for example this one, but our prediction, but our prediction is, let's say, very large, for example here, then the loss will be large, right? So in this case, it also increases linearly. So basically, this is the loss for one training example. So this part here is the cost for classifying the training examples. Now this hyperparameter C that we have here can be viewed as a way to control overfitting. It controls the trade-off between this part here and this part. By minimizing this first part, we want to have a large margin. So we want basically to achieve a better generalization. And by minimizing this part here, we want to classify correctly our training examples. So we want to fit better our training dataset. So now please pause the video and try to think about this question. So what would be the linear decision boundary in this example if we choose the hyperparameter C to be very large? If we choose C to be very large, then in this optimization problem, we are given more importance to this part. So we want to minimize more this part here. And this part means classifying correctly the training examples. So basically by choosing C to be very large, we want to classify correctly the training examples, and we give a lot of importance to this. And by doing so, the parameters vector theta that you will find will give a hyperplane that classifies correctly all the training examples, for example, this one. So when choosing C to be extremely large, this actually becomes like the hard margin problem. It will classify correctly all the training examples, but it will not generalize well. Because as we said previously, suppose that you get a new data point which lies in this part here, and the true label for this data point should be the red class, but based on this classifier, it will be classified as belonging to the blue class. So this classifier does not generalize well. In other words, it overfits the training data. And this is because we gave more importance to this part. We chose C to be very large. Now, if you choose C to be not too large, then you will also give some importance to this part here. So you also want your margin to be large in order to achieve a better generalization. So you will maybe get this hyperplane or line in this example, which misclassifies this training example, but it has a larger margin, so it is able to better generalize. So this hyperparameter C is a regularization parameter. It controls overfitting. and it plays an inverse role to the lambda regularization parameter that you saw in some previous lecture where we talked about regularization. What we saw until now is a linear support vector machine. It can only learn a linear decision boundary or a hyperplane. Can SVM also be used for nonlinear classification? The answer is yes. We can do that using kernel functions and using the so-called kernel trick. So let's see how to do that. In these two data sets, the classes are linearly separable. They can be separated with a line. So we can correctly classify all the training examples just based on a linear model. But in these two data sets, the classes are not linearly separable. This is probably fine for the first data set because we can train a soft margin linear SVM and it will probably have a good generalization error, a low error. But it's not fine for the second data set because the linear SVM, even if it's a soft margin linear SVM, will most likely have a high generalization error. So how can we do in this case if we still want to use support vector machines? Well, a general idea is that the original feature space can always be mapped to some higher dimensional feature space where the classes can be separated linearly. For example, here you can imagine adding a third dimension which makes those two classes separable in a linear way. But with SVM, instead of explicitly projecting our data to a higher dimensional space, we use instead something called the kernel trick in our original feature space. And this kernel trick allows us to compute the dot product between two vectors or two data points in the higher dimensional space, but without explicitly mapping our data to this higher dimensional space. We can do that directly using the kernel function in our original feature space. So here, kernel function k that takes two data points, xi and xj, is just some function that corresponds to the dot product between two vectors, zi and zj. And zi is a higher dimensional vector corresponding to the original data point xi, and zj is the higher dimensional vector corresponding to the original data point xj. So if, for example, we have these two data points, x1 and x2, and if x1 is mapped to a higher dimensional space, let's say that it corresponds to this point, z1, and if x2 is mapped to a higher dimensional space, let's say that it corresponds to this point, z2. Now, if you want to compute the dot product between z1 and z2, then you can do that directly here in your original feature space by computing the kernel k of x1, x2. Because k of x1, x2 corresponds to the dot product between z1 and z2. So basically, without knowing z1 and z2, you can just compute the dot product between them just based on your original feature space, k of x1, x2. So to define a kernel function is just a function k of two vectors, xi and xj. And this function is called the kernel function if it can be written as the dot product between two new vectors. And these two new vectors correspond to the transformation of the original vectors. So k of xi, xj is called the kernel function if it can be written as the dot product between two new vectors. The first vector depends on xi, and the second vector is a mapping of xj. It depends on xj. So if we have a two-dimensional feature space, like in this case, where the classes are not linearly separable, and we want to train an SVM in a higher dimensional space, but without knowing this space, without explicitly mapping the original space to this higher dimensional space, we can actually do that in the original space by using the kernel function, because to train an SVM, we saw that you need to compute the dot product between all pairs of the training examples. And instead of doing that, instead of computing this dot product in this higher dimensional space, you can still do it in the original feature space by using the kernel function. We will talk more about this shortly after. Here you just need to know that a function k of xi, xj is called the kernel function if it can be written as the dot product between two new vectors. The first one depends on xi, it's the mapping of xi, and the second one depends on xj, it's a mapping of xj. To better understand what's a kernel function, let's take the following example. We have a two-dimensional data point or vector xi, and we have another vector xj. And let's say that our kernel function k is defined in this way. So this is a polynomial function. 1 plus xi transpose xj, all this squared. So is this function k a kernel function? To show that it's a kernel function, we need to show this. K of xi xj is equal to the dot product between one vector and another vector, right? The first vector depends on xi and the second vector depends on xj. So let's do this. If you take a piece of paper and simplify this function, you will get this. And we can easily show that this corresponds to the dot product between this vector and this one. Because this transposed vector times this is equal to 1 times 1, this is 1, plus this times this, and this gives you this, plus this times this, and this gives you this part, plus this times this, and this is this, plus this times this is again this, plus this part times this one, and this is this. And you can see that this first vector, denoted by phi of xi, depends only on xi. And this vector, denoted by phi of xj, depends only on this vector, xj. So this one is a mapping of this vector to a higher dimensional space. And this one is a mapping of this vector to the higher dimensional space. So we moved from a two-dimensional space to a space of dimension 6. And since this function can be written as a dot product between two new vectors corresponding to a mapping of the original vectors to higher dimensional space, then this function is a kernel function. Because this can be written as the dot product between phi of xi, this is the first vector, which is a mapping of this vector, right? Transformation of this vector, dot product with phi of xj, and this vector is a mapping of this original vector. It's transformation of this one. A linear kernel function is just the dot product that you know. So k of xi xj equals to xi transpose xj. This is the dot product between these two vectors. So this is a linear kernel. And that's what SVM used originally. If you remember, we saw previously that the training of SVM involves the dot product, computing a dot product between pairs of the training examples. And predicting using SVM involves the dot product between the test data point and the support vectors. So basically, SVM uses a linear kernel, but nothing prevents us from using a nonlinear kernel, like polynomial kernel or other kinds of kernels. A polynomial of degree or of power p is defined as this, and it is a kernel function too. So this is similar to the example we saw previously. 1 plus xi transpose xj to the power of 2. That's the example we saw previously. Another example of a kernel function is the Gaussian kernel, or sometimes it's also called the RBF kernel. And it's defined in this way. So sigma here is a hyperparameter, and this is the distance between the two data points squared. And if you remember the hypothesis function we saw previously for the original simplified SVM, h of x is a new test data point, is equal to this, right? And this involves a dot product between the test data point x and the support vectors, those xi's. And this is basically just a linear kernel. So if we want a nonlinear SVM, we can use another kind of kernel, for example, the Gaussian kernel. And this is the same as if we mapped our data to a higher dimensional space, as we explained previously, right? But instead of explicitly mapping the data to a higher dimensional space, we can just use a kernel function, like for example, a Gaussian kernel function, and the hypothesis function will have the same form as what we saw previously. So nothing really changes. We just use a kernel function here. And that's basically what we call a kernel trick. Just by using a kernel function based on the original data in the original space, it's like if we explicitly projected them to a higher dimensional space, but we don't do that. We just use a kernel function. So to summarize, we can train a nonlinear SVM just by using a kernel function to compute the dot product between data points. And by doing this, it will be as if we projected the data to a higher dimensional space and trained an SVM there. But we don't do this projection explicitly. We just use a kernel function based on our original data. So we don't explicitly map the data to a higher dimensional space. We just use a kernel trick in our original space. And the kernel function of xi(xj) in our original space will play the role of the dot product between the two vectors in the higher dimensional space. So to summarize, we saw that overfitting in SVM can be controlled by the soft margin approach, and this is using the hyperparameter C. And we saw that SVM has a nice math property, so it consists of a simple convex optimization problem, which is guaranteed to converge to a single global solution. So the cost function is convex. And we saw that you can use SVM for linear classification, but you can also use it for nonlinear classification using the kernel trick. And as you know, SVM is a binary classification method, but you can also use it for multi-class classification by using the same strategies we saw in some previous lecture when we talked about logistic regression. So you can use the one versus all strategy or the one versus one training strategy. So in this case, you train one class versus the others. So you have one SVM model for each class. And in the one versus one strategy, you train one SVM model for each pair of classes. So please refer to the previous lecture for this.